This video is for topic 6.5, Energy of Phase Changes. The objective for this topic is to explain the changes in the heat, or Q, absorbed or released by a system undergoing a phase transition based on the amount of substance in moles and the molar enthalpy of the phase change. So in our last phase change diagram, we looked at what was happening in sections A, C, and E. So the times when we were changing temperature but not changing state. Now we're going to look at how we figure out how much energy is associated with just the change in state. So again, notice that the change happens one change at a time. You either change temperature or you change state. So there's a different equation that we're going to use when we go through the calculations for state changes. The equation is essentially the same. Q, or heat, equals M times the heat of either fusion or vaporization. So this is where it depends on what change is happening. So when a substance is changing between a solid and a liquid, we're going to use the heat of fusion. I always remember that because I imagine liquid particles fusing together when they become a solid. So that's how I remember to use heat of fusion. So when it's melting, you're going to increase the energy. So it's going to be positive. When it's freezing, you're decreasing the energy. So it's going to be negative. So the sign of your delta H is going to depend, the number will be the same for that transition, but the sign will depend on which direction it's going. So when it's going from solid to liquid, it's positive. When it's going from liquid to solid, it's negative. And then it's multiplied by the mass, and then that gets you your Q, or your heat. So the units for our heat of fusion and same for the heat of vaporization are usually in joules per gram or joules per mole. So similar to our heat capacities, it's still in typically joules for energy. Sometimes you'll see kilojoules. Like with all things, you need to pay attention to the units to make sure that your units match. But there's going to be an energy, and then there's going to be the mass component as well. When we're going between a liquid and a gas, so evaporating or condensing, we're going to use the same equation, but instead of heat of fusion, we're going to use heat of vaporization. So this one's easy to remember because going from a liquid to a gas is evaporating, so vapor. Similar with the heat of fusion, the sign of your delta H is going to depend on what type of change is happening. So when you're going from a liquid to a gas, it's positive. When you're going from a gas to a liquid, it's negative. So evaporating is positive and condensing is negative. So that depends, that will ultimately determine the sign of your Q. Again, just like with everything else, remember a negative Q means that energy is leaving. A positive Q, that means that energy is entering the system. So it's important to pay attention to your signs because you're going to want to make sure that the appropriate direction is being accounted for when you calculate your Q. Now, if you wanted to calculate both a change in temperature and a change in state, you would do them both separately and then add them together. So it's the total amount of energy involved in that change. So if we wanted to take something all the way from a solid to a gas, you do the temperature change for the solid to a liquid, the temperature change of the liquid, and then the change from the liquid to a gas, and then the temperature change of a gas. You do all the pieces separately, and then you can add them all up. So it depends on what process you're looking at as to what components you need to use. So when we're just looking at a change in state or a change in phase, our equations don't include a change in temperature because temperature doesn't change when we change phases. We're only looking at mass and then the heat of fusion or the heat of vaporization, depending on the change that's happening.